We're even recording. Fabulous. Okay. So we're going to continue talking about protein stability. So about a lecture, and we'll lecture for about an hour and a half, and then we'll get the exams back, and I'll spend the remainder of the time going over the exams. It shouldn't take too long to do that. The exams, as I said in my email, look pretty typical. I mean, obviously there are people who probably wish they had done better. I wish they had done better too. But there's nothing abnormal about the grade distribution here, although it's a little bit more bifurcated. Anyway, we'll talk about it. So just to remind you, if you find errors in grading, go ahead and hold on to those. And then if it's a clerical error, you may bring them to myself or my TA, who doesn't seem to be here today, and we'll take care of it. I'll have to take the exam back, but we'll take care of it. On the other hand, if you have an interpretational issue, then you'll need to submit a written regrade request. So clerical errors are no problem, no hassles. Regrades, we'll have to take a greater look at it. And I'll tell you, I'm always open. It is possible that mistakes are made. They happen all the time. I'm happy to admit them. Want to give you the grades that you've earned. Okay. So last time we were talking about protein folding and stability, and I just want to remind you that stability is defined as the free energy of folding, and it's the free energy of the folded state minus the free energy of the unfolded state. So the directionality of this reaction, because all thermodynamics have directionality, is going from the unfolded to folded state. That's the convention that I have chosen. And just to remind you, those of you who are taking Chem 107A, you've probably seen it in reverse. Everything is the same except flip it with a negative sign. So if we're trying to understand this difference, you have a free energy of the folded, you have the free energy of the unfolded. The thing to look at is what structurally changes between those two. Because if nothing changes, then it's not going to be contributing to that equilibrium difference. The energies will be the same in both states. So when we looked at the properties of both states, wow, that's really weird. Man, oh man. What the heck? Okay. This thing is behaving really bizarrely. Okay, let's try that again. That's really weird. Last time when I put that up, I think you could see all the type on that, I hope. Because I don't remember seeing that before. Sometimes. Maybe I start on that slide, I'll have better luck. Okay. Don't ask me what happened. I'm the faintest. Okay. So if we look at the physical properties of both states, then we can get after what the major differences are. And without going through this table again, I'm just going to summarize for you. The major differences are when a protein is unfolded, all of its interactions are basically with water. Okay? And when it folds up, all of its interactions are either with water on the surface of the protein or with itself, with other residues in itself inside the protein, the parts that aren't exposed to water. That's one major difference. And so what encompasses that is thinking about what the interactions are with water and with the other residues in the protein, what that difference is. That's a delta H because it's about interactions. But there's also the business of what's happening to the water, too, because the water is part of that situation. And then the other major structural difference is the fact that the protein has complete conformational freedom when it's unfolded, and when it's folded, it's really restricted to a very, very few conformations. Okay, and that's entirely an entropic issue. Okay, it's restricted because of interactions with its neighbors, but that's a big deal. So that's all entropic. So really the enthalpic part of this have to do with what the environments around the residues are in the folded and unfolded states, and the entropic parts have to do with chain conformation changes as well as water freedom changes, hydrophobic effect. All right, then we talked about how do you measure this. Well, you find the K. Once you find the K and you know the temperature, you can calculate the delta G. But the problem is the K of most proteins is too large to be measured at room temperature. When the K is very large, you can't measure. You can maybe measure Ks that are between, say, 0.05 to 200 or something like that. How you measure K is measuring the degree of foldedness, because it's a two-state process. When a protein is completely unfolded, it has no secondary structure. By measuring secondary structure, you can measure how much of the protein is folded, because the implication is that it's either completely folded or not at all. Okay? And so that allows you to use circular dichroism, for example. You can also use tyrosine or tryptophan fluorescence. But the problem is you just can't really measure K, even with the great way to do it, so you have to perturb K to make it measurable. And that sounds like a weird thing to do. But what we found is either with heat or denaturants, you can perturb K, measure K over a range of conditions and then extrapolate back to the condition that you want. And we talked about how to do that with denaturants. I'm not going to go through that analysis right now, and you can get delta Gs by taking the Ks that you get from a denaturation experiment and extrapolating back to zero denaturant. Just to remind you how denaturants work, and this is very important, is that they selectively bind and stabilize the unfolded state over the folded state by virtue of the fact that they interact with all surfaces, and the unfolded state has a larger amount of surface area than the unfolded. The unfolded state has a larger amount of surface area than the folded state, and so it is selectively stabilized. If you selectively stabilize the folded state, then you get stabilization of the protein. Okay. All right, and then we realize that delta G doesn't get us very far, because what we really need to know about is changes in interactions and in order, because those are really what have atomic meaning. Delta G doesn't have atomic meaning. And so we have to get after delta H and minus T delta S. And so that means we need some technique by which we can do that, and thermal melting allows us to do that. Basically, we heat up a protein, measure secondary structure changes, measure K over a narrow set of temperature ranges, and from that, in theory, we should be able to extrapolate back to everything normal, and we should be able to get delta H and delta S. Now, what I'm going to tell you is if you take melt data, which is over a very narrow temperature range, it looks sort of linear. You do get delta H's and delta S's, but those are only valid at the midpoint of that temperature, the TM. Okay, that's where you get that information, because around the TM, K's are in the measurable range. However, the problem is that it would be great to be able to use these, but what we found out just by going through a lot of, skipping over a lot of stuff, is that in fact delta H and delta S vary with temperature, and therefore using a sort of Van Hoff approach and a delta G equals delta H minus T delta S approach does not work. Delta H and delta S do vary with temperature when proteins fold. That may be the first time you've encountered that, because in most of the chemistry you've learned, this hasn't been discussed. And so what's going on with that? Well, if we do a calorimetry experiment, we measure the amount of heat we have to add as a function of temperature, and what we see is that we can measure a TM, and we can also look at heat capacities, because heat capacities are telling us how much energy we need to add here to get a certain change in temperature here. And we know that heat capacity and delta H and delta S are related, and if we do a bunch of algebra, we can come up with this corrected way of delta G equals delta H minus T delta S, where we start with the parameters that we know at the melting temperature. That's what this means, delta H at the TM, not times the TM. Okay, this is minus T delta S, T being whatever temperature we're at, times delta S at the TM. And then we have to correct for the temperature we're at using these two sets of terms. This term here is the enthalpy term, and this term here is the entropy correction term. And I think that's where we left it. And so, the consequences of this really big change in heat capacity when a protein folds give us an unusual behavior. If it were DNA, everything would be linear with temperature. The colder it gets, the more stable it would get, but that's not true with proteins. You heat them up to get unstable, you cool them down, there's a temperature of maximum stability, and then they start becoming less stable as you cool it down more. And that's very curious behavior, and we'll get to why that is in a second. Okay, so the question is, we know that there's a change in heat capacity because we have this shaped curve. What do we see? So if we look at scanning calorimetry, we can find out that there is a change in heat capacity. And so let's kind of go back to what heat capacity is. So heat capacity is really measuring how much energy you have to put into a state or a substance in order to increase its temperature, which really means how much energy do you need to put in to increase the mobility of the atoms. Because temperature is a measure of the average kinetic energy. Mass isn't changing here, so it's all about velocity. So let me ask you then, if I have something that has a low heat capacity, what does that mean? Well, it means if I put energy into it, it's almost all going to be translated immediately into increased velocity. Whereas if I have a high heat capacity material, if I put a lot of energy in, I'm not going to see as great an increase in velocity. So the way to really tell you about that is it's really an indication not only of the degree of atomic mobility, but why there's atomic mobility that's different is because in different states you have different restraints on the molecules. In a gas phase, which is the lowest heat capacity of material you're going to run into, you add energy and immediately the molecule can move faster. It's not interacting with anything else. It's just bouncing around inside a container. So all this energy can be basically translated into kinetic energy. On the other hand, if you're in a liquid, now you've compressed those gas molecules. They're always in continuous contact with other gas molecules except at the surface. Okay, they're moving around, so they still have a lot of mobility available to them, but not nearly as much as in the gas. And when they try to move, they bump into something else. Therefore, it takes more energy to move them at the same velocity, or to increase their velocity that much. So liquid has a higher heat capacity than a gas. And then in a solid, of course, we think of the molecules as being fixed. They're not. They're still moving around like this. And if you heat them up, they'll move around a lot more, but they really are restrained in the way that they can move the most. So solid materials have the highest heat capacities, and gases have the lowest heat capacities, unless you're a metal. And metals aren't part of this discussion, but just going to tell you, metals have abnormally low heat capacities because of their mobile electrons. Okay, so that's where we left it last time. Is everyone clear on what gives rise to a higher heat capacity or a lower heat capacity? Everyone good with that? Okay, it's fairly straightforward. So then if we go back to protein folding, okay, and we think about the protein itself, in the unfolded state, would that have a higher heat capacity or a lower heat capacity than the folded state from your viewpoint? Thinking about what I just said. I'm sorry, what? Will have a higher heat capacity or lower heat capacity? Lower. Why? Because it can move. You add energy and it can flop around. Yes, it's covalent linked, so it can't fly apart, but it's kind of like a liquid. All right? When you fold up, now you have compaction of the atoms, and they're now restrained in their motion much more than in the unfolded state, so we expect an increase in heat capacity. And that does make sense. So that's the expectation. Lower heat capacity for the unfolded state, higher heat capacity for the folded state. However, when we actually look at what happens in our calorimetry experiment, we see something different than that. This slope here, this is Q versus T. This slope here is dQ or dH dt, okay, is shallower in the folded state than it is in the unfolded state. This has a steeper dependence. Okay, you have to add more heat to the unfolded state to get the same change in temperature. These are supposed to be capital T's. I'm sorry, they're not time. So actually, the folded state has a lower heat capacity than the unfolded state. That's not intuitive. And where we left this was, what are we missing here? What did I forget, or what did we forget to think about here in this experiment? Because it's absolutely true. What we have said thus far is absolutely true, except it doesn't agree with the experiment. So what's missing? Water. Well, how about just water? Okay, water is missing. We haven't talked about water. A lot of stuff is happening to water. I don't want to talk about entropy because this is okay, but you're right, it's related. Absolutely. Okay, we're not talking about water. We forgot to talk about the hydrophobic effect. Because in the hydrophobic effect, when you have a molecule that's inside the protein, okay, there's no water molecules around it, it's interacting with its neighbors. When you put it out into, and the water is free, when you put it into the middle of the protein, now a lot of water orders around it. That ordered water has a higher heat capacity than liquid water. So when a protein folds, you're taking high heat capacity water, and you're releasing it and turning it into lower heat capacity water as this varies. So what we got, if we've got two different things going on here, they're both happening, but one of them happens to be a lot bigger than the other in magnitude. We do have an increase in heat capacity from the protein chain, but we have a big decrease in heat capacity from the hydrophobic bound water. Okay, or I call it hydrophobic water. And that's because it's more ordered in those structures than it is when it's in free water. So it turns out this effect is about 10 times as big as that. And it pretty much swamps out all of the protein side of it. It really looks like water. So the results of this, okay, is that you have a large negative change in heat capacity, a large reduction in heat capacity when the protein folds due to the release of the restricted water. And how big is that? Well, it depends on how much water you're binding. And we know that the water binding is basically roughly proportional to the surface area that's exposed of the protein. And to a first approximation, with a factor of 2, okay, you can estimate this delta Cp, and there's an estimate that I want you to know. It's minus 12.5 calories per mole per degree K for heat capacity based on a per residue basis. Now you're going to say, well, proteins are different. Yes, they are. And that's why I say within a factor of 2, okay, this is an accurate estimate from looking at lots of proteins. And I didn't make this up, somebody else. Okay. The result of this large heat capacity, which for a complete protein would be something on the order of 2 kcals per mole per degree K, which is big, okay, minus 2, then you have huge temperature dependencies in delta H and delta S. And I have put online a Excel spreadsheet that calculates these things for hydrophobic effect, for protein folding. And what you see is that minus T delta S and delta H vary hugely over the temperature ranges that we're interested in. When we add them together, you don't get a really huge change. And they change in the opposite direction. So basically, it makes them very, very temperature dependent, and they do change from favorable to unfavorable. They have the opposite temperature dependencies, which is really kind of interesting, almost in lockstep. And again, this is how you have to describe the delta G at any temperature. So let's kind of think about this in pieces, because I think trying to take this all in and going through a protein stability curve and looking at entropy and enthalpy in pieces, even with two different components, the protein and the water, becomes complicated. So what I'd like to do is like to break it into a piece. And the nice thing about this is that Cp, H, G, and delta S, they're all state functions, which means we can chop them into any number of pieces we want and get the final result by adding them back together. So what we're going to do is we're going to look at what's going on with water as a function of temperature and its free energy, and what's going on with the protein. So the two ways I want to look at this, and these will be sum up to give us the delta G of folding. Okay? So the first thing I want to talk about is what I call the delta G of transfer, which is also the delta G of water. It's referred to in a number of different ways in the literature, but this is the one I use because this is really about transfer of free energy. We've talked about that before. It's the free energy change when you remove water molecules from hydrophobic residues and release them into liquid water. That's what we're talking about here. And then we'll also talk about the protein folding, which is the delta G of the protein. And this is really the energy difference between the atoms when they're completely exposed to water and be able to flop around in as many configurations as they can find, being compacted into a structure where they're interacting with each other. They're much more highly restrained. Okay, so let's talk about the water side of things, the hydrophobic effect. So this is a not particularly great drawing because it's not really done to scale, but the scale drawing is hard to look at, so I've stretched things out a bit. So first of all, looking down here, forget about my circle, this is the delta G of transfer over a large temperature range. It is negative. This is 0. This is negative. That means it's favorable over that entire range. And that is true. It is always favorable to take greasy things, hydrophobic things, out of water at all temperatures that we will look at. Okay? And what's interesting is the temperature dependence is rather shallow. Okay? And that is also true. There are some temperature dependencies, but it's not great. However, when you start looking at delta H and minus T delta S, you find out that things are quite different. They're very, very temperature dependent. And again, these are very exaggeratedly shallow slopes. If I were to sort of show this to you on scale, this would be kind of the free energy of transfer over temperature range. This would be delta H. This would be delta S. That's how steep they are. Okay? And so let's look at delta H first. Now, what is delta H really telling us about? It's telling us about what are the interactions like of water molecules in the clathrate, which includes their interactions with what they're touching, which is the hydrophobe, which is van der Waals, that's it, and also the hydrogen bonds in the clathrate. Okay, that's the contributors to the enthalpy of the clathrate water. Now, when you fold, and that water is released, how do those interactions in the clathrate compare to those in liquid water? Okay, where the water molecules are still in contact with water molecules, they're still making hydrogen bonds, but they make much fewer hydrogen bonds than they do, in the clathrate, and they're much more mobile. So looking at enthalpy here, all right, we're talking about interactions. And this is mostly about H bonding, because the van der Waals interactions between the protein and the the water and the hydrophobe and the water in itself are really not much different. They're comparable. So they kind of factor out. What we're really talking about here is the difference in hydrogen bond strength of clathrate water versus liquid water. And so what we find is at low temperatures, below 20 degrees C, this is actually an unfavorable process. To take a hydrophobe out of water, we actually have to overcome very favorable hydrogen bonding in the clathrate to create less favorable hydrogen bonding in liquid water. So overall, that's an unfavorable process. We're battling those hydrogen bonds. Now, as we increase temperature, what happens is that everything starts to move around more. And when things move around more, the interactions degrade. Okay? What I mean by that is if there's more movement, if things are moving around randomly more, they can thereby interact with each other with a weaker energy. So I have two atoms next to each other. If they're fixed, they're at their maximum interaction energy. And if they're moving around a lot, then, in fact, they have less interaction energy overall. They spend less time in the configuration than they would here. Okay? And because, and you can say it's a favorable interaction, and making them closer makes them unfavorable, then they'll be biased away from that favorable position. So that happens until at 20 degrees C, actually, the interactions are the same in the clathrate as they are in liquid water. So this is a property of matter, which is that interactions in more condensed states, where there are fewer choices, fewer places to put yourself when you have motion, they're much more sensitive than in situations where there are more options. Liquids, there are more options, so they will lose their interaction energy with temperature, but at a lower rate than more condensed phases like solids or clathrate water. So clathrate water hydrogen bonds get weaker much more readily as temperature goes up than the ones in liquid water. And again, that's a general property of condensed phases. So again, it's 20 degrees, they're the same. And then above 20 degrees, it's actually more favorable to be in liquid water than it is to be in the clathrate. This property sort of confuses people. They say, well, why then would it be in a clathrate? Well, because not forming the clathrate is worse, So clathrates still form. The hydrogen bonds are less good than liquid water, but they just can't sort of, fall off the hydrophobe and leave a vacuum around the hydrophobe. That's not possible, And so they have to be there, all right? So they have less favorable hydrogen bonds above 20 degrees in the clathrate than they do in liquid water, And that's just worse and worse as temperature goes up. So that's enthalpy. So enthalpy is very, very steeply dependent on temperature, and it changes sign right in the middle of a range that we would actually care about, which is 20 degrees. And when I was in graduate school, I learned about the hydrophobic effect, and what they told us is an entirely entropically driven process, because when they measured using calorimetry, the hydrophobic effect had zero enthalpy. Why? Because room temperature is about 20 degrees. And that's where Charles Tanford, who really discovered this stuff, did his experiments and showed that entropy was the major driving force. A guy named Pribyloff came along later and actually found out things were quite different, that there was wildly huge changes in entropy and enthalpy with temperature, and you just had to know what temperature you were at to know what was going on. Okay.
What are you exactly referring to when you say clathrate?
That's the water that's coating the hydrophobe.
Okay, so it's just basically the hydrophobe is trapped within.
Yeah, so we talked about that, I believe, relatively early on. So hopefully everyone remembers that. This picture should be familiar to you. Okay.
Oh yeah.
Okay. So everyone with me on that? Sorry if I. Okay. All right. So yeah, that's the deal. All right. Okay, so that's the enthalpy part, and that's strange because it goes from being favorable to unfavorable in a temperature range that we care about. Minus T delta S, that's a little bit more easy to understand. At low temperatures, we have a really big order difference between the entropically or the more restricted water of the bound water, and then that's released into a freer form. That's a very favorable entropy change. But again, as temperature goes up, both things move around, but the hydrophobic water ends up moving around proportionally more and becomes more and more like liquid water. That's, I guess, the best way to put it. It becomes more and more like liquid water. So the upward trend is due to two things. It's due to the fact that we have a T term also in here, all right, a temperature term, which is going to go up as temperature goes up. But we also have the fact that these two states are becoming more and more similar to each other. The order difference is decreasing as temperature goes up. And then if we could get to 140 degrees, in fact, that's the temperature at which water doesn't exhibit a hydrophobic effect because there's no entropy difference. Now, these are extrapolated temperatures. I know they seem paradoxical, so I'm just going to leave it there. But certainly in the temperature ranges that we care about, it is always favorable entropically to take a hydrophobe out of water because you're releasing it. But that becomes less as temperature goes up. And that ends up being important when we talk about why proteins unfold when they get hotter. Okay, so there's this magic temperature I said, and interestingly enough, this temperature falls out of completely unrelated studies. This is the temperature at which water becomes an ideal liquid. Chemists talk about ideal liquids and so forth. This is the temperature at which it basically doesn't exhibit any properties that are different from other van der Waals liquids, supposedly. As I say, it comes from completely different sorts of work. And why is that? Because at that point, the water molecules are moving around so quickly that they cannot make effective hydrogen bonds with each other. Okay. So overall, for the hydrophobic contribution, you get a very large and negative change in heat capacity because you're going from a restricted water to much less restricted. The delta G for this process is always favorable, but delta H and minus T delta S are definitely very temperature dependent. Minus T delta S is always favorable, but it gets less favorable as temperature goes up. Delta H is unfavorable below for folding, below 20 degrees, and favorable above 20 degrees. Yes? Well, because you always have a more ordered water in the Clathorate, except at 140 degrees, than you do in liquid water. That's it. Is that clear? Okay. So that's the hydrophobic part of things. If you look at the protein side of things, it looks like something we haven't really seen before because this is masked out by the hydrophobic effect. So again, what we have is we have some sort of free energy difference between the protein in itself, folded and unfolded forms of the protein itself. Now this is a little bit hard to explain, but I'll just say it. It's absent of all the water terms except for the water interactions with the protein. What I mean is that we're not considering the water molecules themselves, but we're considering the environment that they create in the unfolded state around the amino acids. So here's delta G. We don't know where it actually crosses zero, to be honest with you. But what we do know is we look at delta H, that delta H is always favorable from the protein side of things. It always is a favorable contribution for the protein to fold in terms of interactions. And I think we have an intuitive understanding that that is true, right? We know the way that proteins drive themselves to fold is, in fact, by creating favorable interactions within the folded state. And these are compared to water. As the temperature goes up, there's more motion, in the folded state, and those interactions degrade. And that's really seen by the upward slope. But that upward slope is also because there's a positive delta Cp. Those are two different ways of saying the same thing, okay? The fact that you have favorable interactions are getting worse in the folded state compared to the unfolded state is why there is a positive delta Cp. Okay? Okay. Now, the minus T delta S term is always unfavorable, so this is always favorable. This is always unfavorable because the protein chain always has way more conformational possibilities in the unfolded state. In the folded state, that will never be good. It gets less and less as the temperature goes down because those folded states become less mobile. Unfolded states become less mobile, but it will never converge on each other. They will never be the same. Even at absolute zero, there will be an entropy difference. So, given that, the upwards curvature is caused by the positive heat capacity change due to the protein. And again, the minus T term forces it up. But what this is saying, actually, is that those entropy differences, again, are getting less and less as the temperature goes up. Okay. So the delta Cp is positive for protein folding, but it's small. As I said, about 1/10 that of the hydrophobic effect. There's very little temperature dependence of delta G compared to the hydrophobic effect. And likewise for T delta S and minus T delta S and delta H. And so those are predictable. I think the thing that's important to understand is that delta H is always favorable. And this, in fact, is really where the structural element or contributions to protein folding happen. Okay? That essentially, this is the contribution of specific interactions with protein compared to generic interactions with water. Okay, if we put it all together, we get this curve. This is adding those two curves together in scale. This is what you see. Okay? So what you see is, again, you see a big, and again, the slopes aren't to scale, so this slope is slightly less than the hydrophobic one that I showed you. It's about 0.9 of it. Okay? It's got a big negative slope because, again, the overall delta Cp is negative. This crosses zero at a temperature less than 20 degrees. And the reason that simply is, remember, we have the water component that's crossing at 20 degrees. We have a negative component from delta H from the protein. You add those together, it's going to shift the water curve to make it slightly flatter and shift it down into the left, which means this is crossing at less than 20 degrees. Okay? Okay. Minus T delta S also looks just like the water curve, except it's a little bit shallower. Okay? And again, it crosses zero not at 140 degrees, but at some temperature actually below the Tm. So minus T delta S changes sign and delta H change sign in the middle of the temperature ranges that we care about. So that's what makes things so complicated and why you really have to think a lot about what's going on, because these things are highly temperature dependent. So again, the consequences of all of this. So in the way, by the way, I got this is I just graphed the components of delta H and minus T delta S and then their sum for the overall. And you can do that too. Okay. So, again, the consequences are very big temperature dependencies for minus T delta S and delta H. That's because of the hydrophobic effect, because it's contributing to this big negative change in heat capacity. They're opposite. And again, the way to think about this is something called entropy-enthalpy compensation, which is just simply that when you have a lot of mobility, a lot of entropic states, you really can't settle into the ones that give you the most interaction energy. So by nature, when things move around more, delta H becomes of lower magnitude. favorable or unfavorable, I can't say. It becomes of lower magnitude. All right? And likewise, when you lock things in to make interactions, you're going to be reducing entropy. Okay? You can't get away from it. So that's called entropy and enthalpy compensation. In general, when enthalpy terms go up, entropy terms go down, and vice versa. Okay. The really big surprise, maybe, well, so you get these three different temperatures that are important, which you don't have with other biomolecules. You get a hot TM, you get a cold TM, and then you get a temperature of maximum stability. The interesting thing is how big delta H is when it's at its maximum. And again, these aren't maximum temperatures. These are ones at 25 degrees C that have been measured for various proteins. And really, in the end, after all of this is said and done, you have very, very little net energy left for protein folding. You have about -5 to -20 kcals per mole. In kilojoules, that's roughly 20 to 80 kilojoules per mole, or 20 to 100 kilojoules per mole. Not much, because one hydrogen bond is 1 kcal per mole. So your typical net stabilization, okay, is 5 to 20 H bonds. That seems odd, considering you have this big structure with lots and lots of interactions, but this is what it is. Okay? And so my question for you is, why so small? Why is it that we have such a small net folding energy for most proteins?
Question. Is that for like a typical protein with hundreds of amino acids?
These are proteins that have been melted, and there's several dozen proteins that are pretty well characterized. So yes, these are substantial proteins. They're not little mini things. But your point is well taken in the sense that it's hard to melt large multi-domain proteins. I think what we know about that is they tend to unfold in pieces. So that's not going to help us. But the numbers aren't that big. It's not size dependent. Any ideas why? Why? There's a generic answer for every why question in biology. Does anyone know what it is? And it's right. It's correct always. Okay. When you ask why things are the way they are in biology, what's the reason? Okay, those are a lot at once. I'd love to hear what you have to say, but raise your hands and speak out. Yeah. It's the easiest. Okay. I think that's on the track. What is that? What do you mean by that? Someone else? Come on, folks. I had a lot to say before, yeah.
That's just the way that nature had it go to.
And okay, that's right. So that's what nature did. But why did nature do that? Did nature say, I only have 5 to 20 kcals per mole to lend to protein for, I'm not going to get an interest back or something like that? But why? So you're right. But why? Yeah.
I guess, I don't know if I'm completely wrong with this, but if you want your protein to be able to get back to a folded state, something that's used in its unfolded state. So if it was exposed to some heat radiation and it was too big of a hurdle to get back, then there'd be no way to.
Okay, that's activation barrier, which is something else. Okay, and you might have some points there, but that's not telling us about why the free energy is relatively small. Again, that's too actually specific an answer. I was looking for a more general one. What's the general answer? All biological questions, every class you ever take, and somebody says, why does this happen? There's an answer. You may not get credit for it, okay, but the answer is definitely correct. I'm sorry? No. Really? Wow, okay. How about because evolution made it that way? Because that's what's required. That's the answer to that question in every single class, because that is what is required for the organisms to function. And why that is, we can speculate a lot, okay, and never be able to prove it, but that's the reason. So evolutionarily speaking, that's what is necessary. Evolution never delivers more, okay, than is necessary. There's no driving force for that, okay? Right? There's no driving force to make things better than they need to be. If they're worse than they can be, then the organism is not fit and it dies, okay? Or the protein is not fit and then it kills the organism. But this is all that's required. And there are all sorts of reasons we could speculate. One, of course, maybe is what you're driving at, is that if you're too stable, you can't be destroyed. And we know that protein turnover is very, very important for the proper functioning of living things. Okay? If you're not stable enough, obviously, then you can't do your job. So why it is, particularly for each individual protein, we could ask very specific questions. But generally speaking, that's what's required. There's no magic here. Okay? That is enough. Okay. Actually, I think that's probably the most important thing I've said today, to be honest with you. All right. So let's look at this curve and think about what's going on at the different temperatures. What's the driving force, or whether the driving force is at different temperatures, and also how are they changing as temperatures change. So this is a lot of information to go into one chart. I just want you to focus on the hot end of this experiment. So on the hot end, we're increasing the temperature. We're at the TM, and we're asking, why is the protein still folding at the TM? What's keeping it folded? That's the favorable terms. These are the terms that are negative, okay, at that temperature. Then also, what are the unfavorable terms? And then how are they changing? Why is it as we increase the temperature do things get worse here? Okay, so let's talk about what's favorable. Well, remember I said the minus T delta S of transfer is always favorable at all temperature ranges. So that's always favorable. The delta H of the protein is always favorable at all temperature ranges. Delta H of transfer, the hydrophobic effect, is also favorable because we're above 20 degrees. So these three factors are all favorable at that temperature. What's favorable is what's always unfavorable is minus T delta S. So to just simply say that T delta S is unfolding the protein is really not correct in the sense that this is changing as temperature goes up. So the second question we got to ask is how are these changing as the temperature goes up? And what I hope you can remember is that minus T delta S is getting less favorable as the temperature goes up. The minus T delta S of transfer is getting less favorable as the temperature goes up. The delta H of the protein is getting less favorable as the temperature goes up. Three things are becoming less favorable as the temperature goes up. And obviously the big negative factor that's pushing them is this one, okay? But all these are becoming less favorable. The only thing that's becoming more favorable is the delta H of transfer, and that's just simply not going to do it. So the protein unfolds. Yes?
So all the things on the right are becoming less favorable?
All the things that say unfavorable, okay? So the arrows here are indicating how it's changing. It's the slope, okay? So this is becoming less favorable. Free energy is going up. This has become less favorable. Free energy is going up. This is becoming less favorable as the free energy goes up. This is the only one that's becoming more favorable as the temperature goes up. So we have three terms getting worse. One, which is the negative term that's really pushing it, and overall protein unfolds at temperatures higher than that. Again, I think this makes sense. We understand why the delta H of the proteins goes up, things are moving around more, and we talked about the entropic terms. Okay. So that's, I think, if not intuitive, at least sensible. Let's go to the cold side, because this is the place where we have the unexpected behavior. This is where the sort of things that apply to DNA aren't going to apply here. So if we look at what's favorable and what's unfavorable at the cold TM, what's favorable is the delta H of the protein. It's always favorable. The minus T delta S of transfer is always favorable. Both of these are getting more favorable as temperature goes down. The minus T delta S of the protein is always unfavorable, but it's becoming more favorable, or less unfavorable, if you will, as the temperature goes down. So we have three things that are getting more favorable as the temperature goes down, but we have one thing that's getting less favorable and is unfavorable at this temperature, and that's the delta H of transfer. And since proteins are unfolding here, we have to conclude this is the reason the protein is unfolding at low temperatures. It's that delta H of the water molecules, the hydrogen bond strength of water molecules, is resisting folding. That's the reason. And it would only happen with water, which is why this doesn't happen with other molecules that don't have a hydrophobic effect, or in situations where you're not in water. Yeah.
So I know that a lot of proteins are stored in glycerol. So how does it
Yeah. So glycerol is a stabilizing agent. We're not going to get a chance to talk about that. It's one of the key parts of the course I cut. But basically, certain solute types of glycerol, one of them sticks to the surface of protein molecules and displaces water from a folded protein. Okay, and it actually makes it more stable. So it changes water properties. The other reason you use glycerol is actually because of ice, which is a completely different reason. So when proteins, when things freeze, you have ice formation around it. And ice can actually physically rip apart molecules. I mean, not break covalent bonds, but it can actually pry them apart. Okay, so when you put in glycerol, what you're doing is you're not forming ice, you're forming vitreous water. So it doesn't have an ice-like structure, and the proteins are much happier than that. So there's really two reasons that glycerol. One is it is a general stabilizer, and two, it prevents ice formation. So generally speaking, just for those of you who handle proteins, quick freeze, quick thaw. Okay? That's the key. You let things thaw slowly, that's generally bad for cells. You let them do that because they don't like to be quickly thawed. But proteins do not like to be slowly thawed. You don't thaw your proteins in ice. Hold them under cold water until they're liquid and then plop them in ice. Okay. So that's the thermodynamic side of things. Very complicated, it seems, but actually can be boiled down to really some pretty simple concepts. If you understand each of the individual contributors here, then you've got half the battle. Any other questions on that? So to summarize, okay, we have very large temperature dependencies for delta H and delta S for transfer terms. Again, this is a large delta Cp. And this large delta Cp really is why protein folding is very temperature dependent and why they're cold TMs. The other thing to sort of point out here is, and there's also very little temperature dependence comparatively for T delta S of the protein and the T delta S of the delta H of the protein. The protein terms obviously are what determines what the actual melting temperature is, the temperature maximum stability, and the delta Gs. Okay, that's protein specific. But a lot of these things are kind of generic, and what I mean by that is that they're similar for all proteins, and when you kind of take a coarse view of it, they scale away with just the number of residues. So, for example, minus all the water terms are really about how much hydrophobic surface you have, what proportion of hydrophobic surface you have. Generally speaking, proteins vary about the same amount of hydrophobic surface, again, plus or minus 30%. And so, therefore, for the most part, you can calculate or estimate delta H and delta S of transfer from just the number of residues. Okay? So that's a generic term. There's nothing specific there. If we get down into the details, there's lots of specifics. But not really so much when we just look at, in general, protein polymer is going to have about the same properties. Minus T delta S of the protein is really about how many residues you're restricting. Again, dependent primarily on the length of the protein. So you have three terms that really, again, in a coarse way of looking at it, are dependent on the length of the protein, the entropy term of the protein chain, and all the water terms. The only thing left that's specific is the delta H of the protein. That's all about the details of what's going on in the structure. And so what I want to say is that it's really the intraprotein interactions that primarily determine what the overall stability state of the protein is. And when you think about that, that's kind of the answer we would expect, right? Protein, we kind of brought up with the idea that protein structures are there to stabilize that specific fold of the protein, that specific shape of the protein, and that they would be the terms that really determine what the exact stability parameters are. You know, when it melts, how much energy is holding it together, and so forth. Okay? Is everyone good with that? Good. Please do the homeworks on this and start working on it. That way, if you have any problems, you can get help on it early, and we can talk about it later. That's a lot to absorb. Okay, so that is what I'm going to say about protein stability. The next thing I'm going to talk about, and we still have about a half hour, is I'm going to talk about how we know a lot of this stuff, how we know about the details of protein folding. That'll be a couple of lectures, so I'm going to do the intro part today. But given it's going to take me a minute or two to set up, why don't you take a couple-minute break, and then we'll get going together.
Just to reiterate, you were saying that. Sorry, I mean.
No, I'm listening. Sorry.
Delta H is getting so unfavorable at low temperatures because it's being more favorable. The hydrogen bond
becoming stronger as the temperature is going down.
Okay. So
and the liquid water hydrogen bond interaction is getting stronger at a faster rate, okay, or at a more temperature dependent rate than the liquid water.
Okay.
So both of them are getting stronger as it goes down. It's a differential, okay? And that's because they're in a restricted position. So as their motion goes down, they're more able to find their best lowest set point.
Restricted.
Well, the restricted
volume. And
yeah.
Then, okay. Perfect. Thank you.
Sure. Hi.
Once they hand the exam, they hand it over, and I'll be going to have an exam at the door, which I can't do. Okay, well, could I go, like, is it possible, like, if I went to, like, 2 hours, would I be able to go outside?
Okay, folks, let's get rolling. All right, so we've talked a lot about generalities in theory, but that's all fine. But what we're really interested in are the specifics. So let's kind of change gears a little bit and talk about how you might analyze protein stability using mutations. So you guys have all heard about mutational analysis before, but we'll still talk a little bit about it. And basically the questions that we're going to try to answer in this lecture, or set of lectures, is what residues in a protein determine stability? Now, the question is, are they all the same? Does everybody contribute the same amount to stability? Why do they do that? What's the nature of it? And how big is the contribution? How much per residue can we expect to be important? And what I'm going to tell you is it's going to be kind of interesting and not necessarily what you expect. So what is mutational analysis? I hope you guys have seen enough of this. I'm going to talk about specifically in terms of our particular work here, but this is also something I'm sure that you have or will learn about in your other MCB classes, the other BMB classes. So what is mutational analysis? Is you make substitutions in a protein, okay, which there are all sorts of ways of doing that, which we're not going to talk about. You then measure something. You ask, what does the mutation do? What does it do the function? In our case, we're going to ask about stability. In our case, we're also going to want to do molecular structures because really to try to understand what's going on here, we have to understand what at least is going on in the folded state, which we can get after through crystal structures or NMR structures. And then looking at what happens to the thermodynamics, what happens to the structure, in particular mutations, we can make correlations between those and come up with some hopefully unifying ways of what holds proteins together. And of course, every sort of type of work starts with assumptions. And one of the assumptions is that you can actually do the experiment. So you need a system in which you can make mutants, do crystal structures, and measure stability. And at the time when this work that I'm going to tell you about was started, and the work I'm all going to tell you about is work on T4 lysozyme, which was done in Brian Matthews' lab starting in 1976 when the structure of lysozyme was first solved, and ended in 2008 when he retired his lab. And this was sort of an accident of history. There have been a number of structural studies done on stability, but very few as complete and wide-ranging as this. So T4 lysozyme is a phage lysozyme. Its job, what is its job? Why would a bacteriophage? Everyone know what a bacteriophage is? They're viruses that infect bacteria. They inject their DNA. Bacteria fill up with phage particles, and then they burst out and go infect other bacteria. So why would a bacteriophage need a lysozyme?
Well, the lysogenic phase is trying to lyse the cell. All the new viruses, they want to leave. They need to bring
They're fully grown.
Yeah. Sorry, I don't.
No, it's okay. I'm just giving you a hard time.
Terminology, but they need to lyse the cell to leave.
That's right. So remember, bacterial cells are covered with a peptidoglycan layer. Okay. Remember, lysozymes cleave sugars in peptidoglycan. Okay. So all bacteria have a membrane, and then they have this peptidoglycan, and some have an outer membrane on top of that. Point is that it's like a netting around the cell, and you have all these bacteriophage particles inside the cell. They can't get out because they're held by the net. So let the lysozyme out. This guy actually has two different lysozymes. Not all phages have this. This has one for getting in also. Okay, because it actually injects its DNA directly into the plasma membrane, the inner membrane, and has to get through the lysozyme. So there's another something called the base plate lysozyme, but this is the lytic lysozyme. Okay, so that's what it does, and it lyses bacterial cell walls, just like hen egg white. Okay, so why use this one? It turns out that this is one of the first. In 1976, there were not very many crystal structures done of molecules, and hen egg white lysozyme was one of the first crystal structures done of an enzyme. Okay, and then the thought was, evolutionarily, what's going on with phage lysozymes? And it turns out it just crystallized really easily, and as I said, they were able to solve the structure very early on, and they started asking questions like, well, what does this have to do with stability? Because they were interested in mutants of T4 lysozyme that had been identified by other researchers in their milieu, and that's what got them onto this. So, pretty much about 3,000 T4 lysozyme mutants were created over that time period. About 1,500 to 2,000 of those were melted, and their thermodynamics were determined. And much of that data got lost, but I think it was assembled by some later postdocs. And about 1,200 structures were done, of 600 of which were published in the Protein Data Bank. That, by far, is the most comprehensive data set of structure and stability that was ever done. Enzymatically, unfortunately, it's not easy to measure activity quantitatively, so that part got left out. Oh well, that's life. So that's fantastic. So let's talk about these guys a little bit. So what they do is they infect bacterial cells. More of them get made, and they bust out. Now, if you take a petri dish and you plate on it a confluent layer of bacteria, and then you infect those bacteria with a bacteriophage, what happens is that you get little cleared circular areas called plaques. And those are just the areas where the cells have been lysed because they're full of phage particles by the lysozyme. And so that would be the picture you'd see right here. Okay, that's what they do. This is a lawn of bacteria. Those little holes are called plaques. Now, T4 lysozyme, if you then take that plate and expose it to chloroform vapors, kills the cells, but also renders them more susceptible to lysozyme, and then the lysozyme diffuses out from the cells and starts to make bigger lysed areas. And so the size of these so-called halos are indicative of activity. So this guy here is the wild type. This one here is an impaired activity or stability mutant, and this is a more active protein than a wild type. Okay. So, nice system. And as I said, this is one of the first systems where people had worked on getting overproduced versions of the protein, were able to do mutagenesis and actually grow crystals. That was just not possible with very many proteins. Before that, again, that's an accident of history. It could have been just anything. But subsequently, everything I'm going to tell you has been repeated with other works and more or less has agreed with the work done here. So I'm focusing on this, but in no means do I want to tell you this is the only work that was ever done. Lots of nice work by Dave Shortall on staph nuclease, a number of people on RNase T1, Buzz Baldwin, who's not a relation of mine, former Stanford professor, and so forth. There's just a lot of great stuff. So, the first question that Tom Albert wanted to ask was, which residues are most important for stability in a protein? Whoops. So the question I have for you is from a phenotypic point of view, okay? And remember, at that point in time, making site-directed mutagenesis was actually incredibly difficult. And also, if you're presented with an entire protein sequence of 164 amino acids, where do you start mutating residues? At that time, making mutants was difficult. It wasn't very easy. And if you remember, the people who were studying metabolism, 20 years before, 30 years before, when they're asking, and they didn't know what a genome was, much less what genes were, what genes are involved in, say, biosynthesis of a particular amino acid, they didn't go in and start knocking out individual genes because they had no idea. So what did they do? Okay, how do you tackle a problem that's complicated where you have lots of possibilities and you don't even know where to start? Okay, what's a general approach, okay, to solving that problem? It's been done countless times in all sorts of levels, from genes down to amino acids. What's the first thing you need to do? You try and understand the basis for a certain phenotype, okay? And so, what's the first thing you need to do? Okay, let's talk about amino acids. I know you learned this in 101. Okay, so histidine biosynthesis. You've got bacteria, and you want to identify all the genes involved in histidine biosynthesis. How do you do that? Maybe you didn't do histidine, maybe you did something else. How do you do that? Yeah. Double mutants.
Or single mutants and see where it stops.
How do you make those mutants?
Right, it's hard.
Well, actually, it's really easy.
Oh, you just shoot X-rays at it?
Yeah, you just blast the heck out of the thing, okay, with mutagens. Okay, you have no idea what you want to mutate, so you just mutate everything. Well, not all at once, but in bits and pieces. You just generate a whole lot of mutants, okay, and then what do? Now you have a whole lot of mutants. How do you do that, though? Do you take each one and then do careful biochemical assays on each? What they do in histidine biosynthesis case? Okay, what can you use to identify in a massive, let's say you take E. coli, you completely mutagenize it, and you want to identify only the E. coli that had impaired histidine biosynthesis. Yeah.
Oh, you plate them on like histidine and histidine?
That's right. You basically have a phenotypic screen. You have to develop a phenotypic screen that allows you to identify them. In the case of histidine mutants, they said plate them on histidine. If they live, they're clearly not mutants. They require histidine to live, but they don't live without it. Then they're clearly impaired in histidine biosynthesis at some level. And then the rest of it's genetic mapping, which we're not going to talk about, okay, because we have sequencing. So what Tom Albert did is he said, okay, I'm going to make a whole lot of T4 lysozyme mutants. And he did that by dumping mutagen on T4 phages. Then he had to screen. What's his screen? Okay, so we're looking now for a stability mutant. We're not looking for a null because a null is dead. Okay, and all sorts of reasons things should be dead that have nothing to do with stability. Okay, but what's the phenotype of a mutant that's unstable? You actually know this, but you probably haven't connected the dots yet. Yeah.
Do you like
You could do that. That would be that's a screen, okay? But that could be done. It wasn't done, okay? It could be done. And I'll tell you the reason why. Halos are actually, unless you have a pure kind of culture, they're very variable even within one type. But you're on the right track. Okay. Yeah. What's a stability mutants phenotype? How do you identify a stability mutants phenotype? Let's think about it. Okay. I have a protein. It melts at a certain temperature. What's an unstable protein look like? It melts at a different temperature, right? Like which way? Higher or lower? Lower. This is still not making... So is there anything time that you've learned about mutational screens that involve temperature? Yeah. Like a temperature sensitive. Tell me what the phenotype of a temperature sensitive is.
Well, it's like either a certain temperature, usually over a certain temperature, it doesn't do something, and then under, it can use like regular reactions.
Absolutely. That's a stability. Okay, at low temperatures it behaves normally, which means you haven't screwed it up, because many mutations just screw things up. But at high temperatures, okay, it doesn't work. That's a stability mutant. The TS mutant is one of the oldest conditional mutations out there. Okay, so they didn't have to make this stuff up. Okay, they knew what this phenotype was. So that's what he did. He mutagenized T4 phage, screened them for temperature sensitivity, which in this case is plating them on, creating replica plates of a bunch of plaques, and wherever there was a plaque on a 30-degree plate, but not on a 42-degree plate, that's a TS mutant. So he did that and isolated a bunch of them and then sequenced them. Okay? And then he mapped them onto the structure, which had already been done. This was done in the early 80s. And this is his result. Okay? You may say, what the heck? Okay, so what this is, since we've had crystallography now, this is a plot of residue number for T4 lysozyme and this thing called the B factor, which I told you about a little bit of time ago. The B factor is a measure of really how well defined an atom is in a crystal structure. And what causes atoms to become less or more well defined is how well ordered they are. Remember, molecules are not actually rigid, they are moving. And in some parts of the structure they move more, and other parts of the structure they move less. Okay? And so what he did is he just looked at the B factors of all the residues, averaged over each residue. So each one of these points, okay, along this jagged curve is the average B factor for a particular residue type. You can see there are lots of low mobility residues and lots of high mobility residues. And what he found was, well, what? Where are all those stars mapping to? What part of the structure? The mobile part of the structure or the less mobile part? Less, okay? The less mobile part of the structure. So that was the title of the paper, actually. Temperature-sensitive mutants map to the lowest mobility part of the structure. Now, that sounds anticlimactic. It is, okay? But people were very cautious in those days, all right? So let's go on to the next one, and we'll find that, in fact, this result makes complete sense. Okay, another way to attack this is using specific mutagenesis. This is 10 years later. Technology is hugely improved. Site-directed mutagenesis of oligonucleotides was possible and done very easily. And there were much easier ways to do all this stuff, and you didn't need to do phenotypic screens. So what Kai Zhang did is he marched through various parts of the T4 lysozyme structure, in this case a helix, going from this residue to this residue, okay, shown here. And he just went through one residue at a time and converted them to alanine. Okay? That's called alanine scanning. Why would you convert something to alanine? What are you asking when you use an alanine mutant to dissect something? What role are you trying to assess about that residue? So why use alanine? Okay. No, you're on the right track. Does anyone else want to tackle that? Then why alanine? What's missing? It's the best in alpha helix, which turns out means you're not going to do anything bad. You're right. You don't want to, when you make a mutant, you don't want to introduce anything new, right? If you were trying to ask what's the role of the side chain, which is what is really after, what's the role of a particular residue identity, it's the side chain, right? And so taking out the side chain is a very harmless thing to do. And if nothing happens, then that side chain isn't very important. If something happens, then you can say there's something important there. You start doing other things like glycine, which is what people often come up with. Glycine does all sorts of things to the backbone that we're going to learn about that we don't want to have happen. So we're really asking, if we take a side chain out and something happens, then we mean that that side chain is important. And alanine, as you pointed out, is the simplest replacement that doesn't add anything new. Right? So you were saying it. I just wanted to hear it in slightly different phrases. Okay. So this is what they did. So they marched to the helix. And then he measures stability. And what I'm going to tell you is that this is a graph out of his paper, which uses the delta G of unfolding, not folding. Okay, and we'll get to what that means in a second. But these are stability differences between wild type and mutant. And only in this case am I going to show a negative number being less stabilizing. Okay? But what you can see is 6 out of 9 of these mutants don't do anything to stability. They don't do anything. One of them slightly stabilizes. That's its own special case. I'm not going to talk about it. But 2 of these guys are pretty darn destabilizing. 4 kcals per mole, 3 kcals per mole. The overall delta G of folding for T4 lysosome at this temperature is about 15 kcals per mole. So these are individual replacements. And if you look at where they're located, all the ones that change the stability are buried, and all the ones that don't are exposed to water. They're on the surface. So we have these 2 results. One is that the least mobile residues are the ones that are most important for stability. The other is that the most buried residues are most important for stability. How do we reconcile these different results? Do they need to be reconciled? Are these different? What part of the structure is least mobile? The inside, right? Because it's touching other protein atoms. Okay? So maybe least mobile and buried are the same. So motion is definitely restricted by interactions with neighboring residues. And the residues, that are involved in interactions, as we said before, the folded state interactions are the most important. Okay? And basically the least mobile residues are the most buried. So in fact, these guys are really the same. And what I'm going to say the generality really is that only residues whose environment changes when the protein folds can contribute to stability. If the environment doesn't change, they can't contribute because the free energy contributions of those are really the same in both environments that they're in. And which influences you look at depends on how you're asking the question, and we'll talk about that. So strictly speaking, if you're on the surface, you're really in a similar environment that you're in when the protein is folded. When it's unfolded. So, this is really important. If you want any big generality to remember, that's it. And again, it depends on how you parse this, what aspects you look at. But generally speaking, that's the case. Okay, in the last little bits, I want to start on talking about how we might think about how to look at changes by mutations and how we might very simply figure out what we'd expect them to do. Really, the picture looks like this. I have these free energy diagrams which happen to like. Okay, down here, over here is the free energy scale, absolute free energy, which we don't know, but we know what it changes. And below here is the reaction coordinate. That just simply means that one state is different than the other. And we're not going to talk about the details of this. And what we're interested in is what's the energy difference between these 2 states. Okay? Now, if this is the unfolded state and this is the folded state, then this is a situation where it's a negative delta G of folding that's favorable under these conditions. Why? Because we're going downhill, if you really just want to be simple about it. Okay? On the other hand, we also could talk about conditions which are like this. Okay? Where, in fact, the folded state free energy here, is greater than the unfolded state, and this would be unfavorable for folding, and there would be a delta G. But it's this difference that we're trying to measure or trying to understand. So the sort of way we go about thinking about how to analyze stability is you draw the diagram because it's entertaining. Then you look at what happens to the U state free energy, which you can figure out from the mutation pretty much knowing what you already know. You can look at the U state because there's nothing detailed there. All U states are roughly the same. And you can generically say, if I make this sort of substitution in any U state, I'm going to get this change. And you can actually do that with pretty good surety. You can't necessarily get the magnitude, but you certainly can get the direction. Then you ask yourself, given what you know, what do you expect to change in the folded state free energy? Now we've dealt with the one on the left. Now we're going to deal with the one on the right. They're both going to change. And then we're going to ask what happens to that gap between them. That's the delta G that we're interested in. So we have to know what happens in the folded form and in the unfolded form before we can even really get after this. And that, I think, for most people is not necessarily intuitive. Okay, I think most of us look at the folded state and basically say, oh, I can tell what's going to go on. But if you don't think about what's going on in the unfolded state, that doesn't work. Okay, so a couple of conventions. I'm going to use this term a lot. So the delta G of folding, it's change in the delta G. And what it is, it's the difference in the free energy of folding of a mutant minus the delta G of folding of a wild-type protein, unmutated protein. And basically using this sign convention, a negative change, a negative delta G is favorable, and a positive delta G is unfavorable. Okay? That's just how it is. For folding. If we're going to unfolding, it would be the opposite direction. Okay, so then comes the fine print. Remember those drug ads where they have the person speaking really fast? This is the really speaking really fast case. Only valid for given temperature TFURF because the input needs to change the delta C. Delta H to us. Sorry. Okay. So this is true, okay, but it's only true for really a given set of situations. And this is very, very important. It's hard to tell you how important this is and have it make it stick because you don't do this stuff, but take it from me. Okay, these measurements that I'm going to tell you about are only valid for a given temperature, which we call the reference temperature. And anything you read will talk about reference temperatures. This is important because this difference is only valid at that temperature. And that's because of the delta CP and how it changes delta H and delta S. As I said, what do you usually choose as a reference temperature? Well, you want to choose the temperature at which you know the delta G for at least one protein, which is usually your reference protein, usually the wild type. So typically speaking, the reference temperature is the TM of the wild type. Why? Because you know delta G at that temperature, it's 0 for that protein. But occasionally, and this is a fine point, but I'm still going to bring it up, some proteins don't melt very well. And what I mean by that is that they're not well behaved. And that means that maybe their temperature dependencies are really odd. And so to get around worrying about that, you can choose them, the one with the ill-behaved melting behavior, as your reference temperature. And then you at least know its delta G is 0 at its TM. Okay. And the farther you get from your reference temperature, or the TM, the less sure you are about everything I'm telling you. And what I'm going to tell you, which is upsetting, but you're just going to have to swallow it, is the fact that everything I'm telling you could be reversed at different temperatures. And what's the point? The point is that we still can understand this in a qualitative way, and this is how the field understands it, but I would feel really illegal, okay, or deceptive if I told you it was all a nice thing you could tie a bow around and not think about. So I'm going to tell you now, tie a nice bow around it, don't think about it, but just remember I told you this. So, okay. Let's talk about some real mutations. In fact, let's talk about a mutation where we take a surface residue when the protein is folded, is on the surface, okay, and it's a leucine. Now, right away you're going to go, oh, leucine's never on the surface. Sure it is, okay, it is on the surface, just not often, okay, and usually if it's on the surface, there's actually a reason for it, because it's not really good for solubility. But this does happen, I'm not making it up. And what we're going to do is we're going to change this leucine into an alanine, where we basically just chopped off this isopropyl group, okay? And so the question is, what's going to happen to stability in this case? So we draw a picture. Here's our unfolded wild-type free energy. Here's our folded state wild-type free energy. And here's the delta G. It doesn't matter what it is. All we want to know is what's happening to that difference. So let me ask you. If I take leucine and alanine, how's that going to change the free energy of the unfolded state, and why? Would you expect the free energy of the unfolded state to go up or go down? Remember, we're just talking about the unfolded state here. We're not talking about the folded state. What happens to the free energy of the unfolded state when you make a hydrophobic side chain small? Okay, first question is, who is that side chain interacting with in that state? Water, right? We already said all the residues interacting with water. Which is more favorable? Leucine interacting with water or alanine interacting with water? Alanine. So what happens to the free energy of the unfolded state? It goes down. You knew that. Okay? You did. Less nonpolar surface exposed to water, lower free energy. Okay? Now, what about when the protein folds up? This is the surface residue. What's the environment like around a surface residue in protein? Who's its primary interactor? It's on the surface. water. Okay? Which is more favorable, leucine exposed to water or alanine exposed to water? Alanine. Okay, that free energy is also going to go down. What about the difference between them? What about delta G? Is it different from the wild type? Not substantially. Because both the unfolded state and folded state free energies go down. They go down more or less in lockstep. That's no net change. Therefore, if we go back and look at Kai Zhang's result, okay, all the surface exposed residues, no change. It's not because there's no change in free energy. There is, but it's the same for the folded and the unfolded state. Remember, environment hasn't changed. The effects of the mutation on the interaction of the environment haven't changed. Therefore, no net change. Now, is this always like this? Most of the time it is. 70% of the mutations made on the surface of proteins, okay, are they don't do anything obvious to stability. Okay? Since the environments are the same or similar in both, there's very little net change. Okay? Okay. All right. I'm almost tempted to hold this one till tomorrow. I will. Okay. So let's stop, and I'm going to hand out the exams. Yes?
How do we take into account proteins interacting with that protein or that
Well, we're not talking about that.
Okay, so we're always interested in the protein.
We're going to talk about soluble proteins. Membrane proteins is really hard to measure stability. People do it. It's tough. The rules are slightly different. Okay. So we'll stop there.